All right, let's start again here. So again, this is exact, this is not exact. So this, the average is probably between 16.5 and 17.4, somewhere around there. They just decided to express it at 17. All right, algorithm to solve a quantitative chemistry problem. In other words, analyze the problem statement, determine the given quantity, describe the property of the given quantity, describe the property of the wanted quantity, state the unit of the wanted quantity. Step 1. Step 2, identify equivalences or an algebraic relationship that may be needed to solve the problem. So in other words, we look for converting factors. So step 1, just lay out the problem. Step 2, find the conversion factors. Step 3 is kind of make a map where you want to go. And sometimes we skip that. Sometimes we don't have a map, we just go. Step 4, check the solution at 2 levels. Does it make sense? Is the value reasonable? What was learned? And so that's the dimensional analysis approach to problem solving using conversion factors. So let's calculate the number of weeks in 672 hours. Apply the quantitative solving procedure. And so we'll do this step 1. Let's do this on the board here. So what I have is I have it given 672 hours. Each hour is the abbreviation for hours. So 672 hours. Eventually, I want this in terms of weeks. Weeks. How many weeks is that? And so the thing is, I could come up with a map, like a mental map, but sometimes I just don't have a mental map for this. I don't know how to approach this. And this is the way I do every dimensional analysis. Sometimes I know exactly how I want to map it out, but that just comes from experience. When I'm just starting off with dimensional analysis, I don't know where I'm going. All I know is this. I want something that gets rid of hours. I need something that gets rid of hours, so I need to relate it. The best thing is if I can go to hours of weeks, but do you know how many hours there are in a week? Okay, you might have it memorized. If you have it memorized, you can use it. But I don't. But I know how many, not enough. I know how many minutes there are in an hour. So if I do this, let's go. If I go 60 minutes in an hour, that works, right? But then I have to ask myself, am I getting closer? Am I getting warmer, or am I getting colder?
Colder.
Yeah, I think I'm getting colder because I don't want to be going to minutes. So this sometimes this happens, and we end up at a dead end. But it's no big deal because it happens all the time. People end up at a dead end. So I don't like this one because it seems like I'm getting colder. So I need something else. Yeah, let's try that one. That there are going to be 24 hours in one day. That's exact. And then, then we need to get rid of days. So this one, you know that there's 7 days in a week. 1 week. Is that exact? That's exact. And so the days cancel. So what we've done is we've strung together 2. This is what I mean by 2 or more. Sometimes we just keep stringing or adding them along. But sometimes we add these along, and by the 4th one we're at a dead end. But it's not fatal, it's not like a dead end where you're going to be trapped for the rest of your life. What you do is you just back up and then start over again, You just back up a step, or back up 2 steps, or back up 3 steps, and then see if you can take an alternate path. So here we hit a dead end. Well, we're getting colder, so because the next one would be minutes, and getting minutes to weeks would be harder to do. And so this works out. And so this is the strategy here. The strategy is this. I don't necessarily map it out. I don't map out the conversion factors. I just try to figure out the conversion factors once I need it. So my strategy is different. I don't do this first. I do that unless these are given in the problem. If they're given in the problem, I do it first. Since these weren't given in the problem, these we had to find elsewhere, then I start off with this, trying to cancel out hours. And so how many weeks does that come out to? Actually, it comes out to 4 weeks. Now, this is tricky. Okay, is that exactly 4 weeks or approximately 4 weeks? Is it exactly 4 weeks? Okay, then the way we do it is this. I mean, we punch it out in the calculator, and it came out exactly 4 weeks?
Yeah.
Okay, then we have to do something here. So if we said in exactly 672 hours, there would be exactly 4 weeks. Because these two are exact. This is exact. This is exact. But what if somebody said, well, it's around 672 hours. If it's around 672 hours, there's uncertainty associated with that. It's not pinpointed, right? And so if somebody asks you about how many weeks are there in about 672 hours, then you'd say there's about 4. And so when you say 4, it could mean different things. It could mean exactly 4 or approximately 4. If it means approximately 4, what would you say? Here, if they said approximately 672 hours, although that's pretty precise, in terms of language, but if they said approximately 672 hours, and then you say, oh, that's about 4 weeks. When somebody says about 4 weeks, then they're talking about 3.5 to 4.4 weeks. And so if they're being very precise here, 672, but you say, that's anywhere between 3.5 and 4.5 weeks, that's too big of a window. Does that make sense? Because the uncertainty here is maybe of an hour, 672 plus minus an hour. Right? But half a week, that's not plus or minus an hour, that's plus or minus many, many hours. Does that make sense? And so it doesn't quite conform. And so what we do is this. Oftentimes, these numbers are measured, and so it just so happened to work out. But let's say it was 673. If this were 673 hours, would it be exactly 4 weeks? No, how would you express it? Now, the way we express it is this. This is what we call 3SF. SF stands for significant figures. Therefore, if we have 3 significant, and these are exact. Exact means we have infinite SF. Whenever we have exact, it's infinite. So this is like 24.000, an infinite number of zeros there because it's right on. But over here, if we have 3 sig figs there, then this should be expressed in terms of 3 sig figs. And so this should be expressed as 4.00 weeks. Right? About 4.00 weeks, then that means it's anywhere from 3.95 up to 4.04 weeks. And that range gives us our uncertainty there. And so,
Do you always use the most amount of significant figures?
You always use the least amount, because these are infinite here, so the least would be 3. There are more rules, but we'll hit those other rules as we go along.
So even if it's exact, you want us to put it in the...
No, if it's exact, then we can just say exactly 4 weeks. But we'd have to state it as being an exact number because, it says, how long did the drive take to San Diego? Oh, it took 4 hours, right? Because traffic. Oh, they must be talking exactly 4 hours?
It's about 4 hours.
About 4 hours, right? And therefore, if it did actually take exactly 4 hours, then you would say exactly 4 because it's unclear, But based on the context of the answer, you'd say that's got to be approximate. That can't be exact, right? Well, that makes math a little bit more complicated, than your straight algebra. In your straight algebra, you might not have worried about this, the meaning of the numbers. This was what was learned should be, what was the meaning of the numbers? What do the numbers mean? What distance expressed in miles would an automobile travel in 3 hours at an average speed of 62 miles per hour? And so this, the way we answer this question is a little bit tricky. And it's a little bit ambiguous. Well, the math isn't that bad, but what do I mean by 3 hours? Do I mean exactly 3 hours, or do I mean approximately 3 hours? If I mean approximately 3 hours, then I'm looking at 2.5 to 3.4 hours. You know, somewhere. In other words, when we're dealing with science, we usually take the number, cut the last digit, cut it in half. So it'd be 3 plus or minus half. Out, half an hour. And so, we have that uncertainty there. But in a question like this, we might be more interested in exactly 3 hours. In exactly 3 hours, traveling approximately 62 miles an hour, what is the distance? And so we don't, we like to keep certain numbers exact and throw all the uncertainty into others, to other numbers. And so, do you know how many liters are in a gallon? You could just be approximate. A liter is about a quart, 4 quarts in a gallon, so maybe about 4 liters in a gallon, right? Now, what would we say? You start thinking about these things when you're thinking about these equivalencies. Would you say this? There are approximately 4 liters in approximately 1 gallon. There you have uncertainty in the liters, and you have uncertainty in the gallons, which is like double uncertainty. So normally what we say is this: there's approximately 4 liters in exactly 1 gallon. So exactly 1 gallon has approximately 4 liters. That way we throw all the uncertainty into the liters. And so liters is going to be between 3.5 and 4.4 liters in a gallon. Does that make sense? And so this is the way we think about it. And so in that context, we might be thinking in exactly 3 hours, how far can I go if I'm traveling approximately 62 miles an hour? And so here, this is, okay, we're given 3 hours, and we want to know the distance to travel. But we're given 62 miles an hour, and so we're given this, and we're given 62 miles in 1 hour, or in 1 hour, we'll travel 62 miles. So those are the 2 conversion factors that we can get from this statement. And so this problem includes our given plus a conversion factor here that we can use. Well, in this case, we can use this. So we're given 3 hours. And so we're going to say this is exactly 3 hours. If it's exact, we say it has infinite number of sig figs. That is, there's no uncertainty. It's exactly right on 3.000000. And the number of zeros, it's like this. If you go get 1 gallon of gasoline, you might say this: 1 gallon. 1 gallon of gas. But that 1 gallon is ambiguous, because if this were exact, we would say it has an infinite number of sig figs, so it'd just be like this, and it would go on from infinitely. It would be 1.000 right on. Versus just a measured value, which would just be 1 gallon. It would be 1 gallon plus or minus, half a gallon. We take half as the smallest unit here. And so this would be anywhere from about 0.5 to 1.4 gallons, in terms of range or uncertainty. And therefore, different numbers have different meanings. So a lot of people will say 1 gallon, are these 2 numbers the same? And a lot of people will say these 2 numbers are exactly the same thing, because they're saying, okay, I have 1 gallon. If I got 1 gallon, I got 1 gallon, right? But to a scientist, these 2 numbers are not the same. You might think, hey, what's the difference? 1 gallon, 1 gallon. The difference is in the uncertainty here. And so if I have 1.0 gallons, we call that much more precise. You know, much more precise meaning, you know, precise, it just means that, you know, there's less range and uncertainty. You know, imprecise numbers have a big range of uncertainty. The more precise, the narrower the range of uncertainty becomes. That's one way of doing precision. And so if you're going in for surgery, you want a surgeon who has high precision. You know, that they aren't just like a half-inch off. It's okay, close enough. Right? Here, it's the same thing. This is a much more precise number, and so when people think about this number, they're thinking between 0.95 and 1.04 gallons, versus this number, which is 1.5 to 1.4. Much less precise, although a lot of people take these as the same. They aren't the same. And so this is the other thing we have to think about. Now, for 3 hours, you know, there are different ways we can think of this. This could be 1 sig fig, which isn't that precise, you know. This is what we call 1 sig fig. So this is 1 sig fig here, or 1 s-half. This one would have 2 sig figs. So it'd be a little more precise. Well, since this is ambiguous, this is 1 sig fig or infinite, and so if it's left to us, we'll just define it as infinite. I'm going to pick infinite. So in exactly 3 hours, how far can we travel? And so in exactly 3 hours, well, I need to get rid of hours. So is there something that gets rid of hours? Yeah, 62 miles. And so here, this is not exactly 62 miles, right? I don't travel exactly, it's just approximately 62 miles. So this is what we call 2 sig figs here. And therefore our answer is going to be valid to 2 sig figs. So 3 is going to be 186 miles. All right, so 186 miles is being a little bit too precise here. And so I have to do something. Okay, this is 3 sig figs. And so, you know, because of the uncertainty in the 62, I'm going to have uncertainty in the miles traveled. Therefore, I need to write it as. So the easiest thing to do for this is to put it in scientific notation. 1.86 times 10 to the second miles.
Isn't that still 3 sig?
Okay, this subscript value means it's an extra digit. It's not allowed. And so what I have to do is I have to drop it and round it. So this comes out to 1.9 times 10 squared miles, or 190 miles. Now 190 miles is confusing because this could have, this could be exact. You know, there's a question mark. It could be exactly 190 miles, or it could be 2 or 3 sig figs, depending on the precision. In this case, it's 2. So usually when you have a number like this, then the 0 doesn't count. So that's why some people write it scientific to make sure that the correct precision is given to this. And so what we want is we want the answer to reflect the precision of our givens. So here, you know, like I said, I'm just going to be consistent through. You know, this way I'm not going to change it. We don't have to go back and correct it, because later on we're going to learn more about sig figs when we hit the topic. But I don't want to come back and say, okay, we got to fix this problem. I just want to do it right the first time. Yeah.
The step where you write the subscript under the extra digit on the exam form, should we skip that step?
No, I'd like to, I want to see what digit you're dropping. This one you could skip it if you wrote this.
Okay, so as long as we have that.
Yeah, then as long as I see what digit you're dropping, that's better. I need to see what digit. A lot of people will skip this step, and just go right to this.
So if you have 62 miles, about 62 miles an hour, that accounts for anything 62 plus or minus 25 miles, right?
Yeah.
But if you take 3 hours times 0.5 miles, and you only have 1.5 miles, and 186 plus 1.5 doesn't equal 190. So wouldn't 190 be an overestimation?
Yeah, it would be overestimation, right? And that's the problem with significant figures is just to get you thinking about. It's just to get you thinking about precision in science, but that's not how scientists really do it. You know, it's close, but not exactly. And so this would be a little step. Rather than diving head first into the Olympic-sized swimming pool, we're going to start off in the small pool and try to do laps on that or something like that. You know, the proper way of doing this is we need calculus to do it.
What answer would you want on the 186 or the 190?
190, but the previous question was, I need to see both numbers. I need to see what you had before you rounded and after you rounded it. 190 would be the correct. This is the proper way of dealing with it. It's called propagation of error. Down here, propagation of error or propagation of uncertainty. Unfortunately, the math involved in this is beyond the prereq for this class. The math is not hard if you've had calculus. If you had calculus, then we take these things called derivatives. We take that. But you know, the answer that we're going to get is so close to what we're doing, and this method here is so much simpler that we're just going to do this. But later on in physics, you'll probably do propagation of errors, or any upper division class, you're going to do propagation of errors once you've had calculus. Some of you have probably had calculus if you deal with this already, but it's just a much better way. Sometimes it totally overestimates or totally underestimates the amount of error that you have using significant figures. Especially when we throw in addition, it can totally overestimate or underestimate. And so this is one of those things, you know, this is not the law of the significant figures. These are the rules of significant figures. And rules have a lot of exceptions that you have to be aware of. Okay? So just learn the rules. Then when you get to the calculus, then you can kind of ballpark it in your mind, you know, the magnitude of the error, and you can do a quick check to see, because when you get caught up in all the math, sometimes you lose sight of the magnitude of uncertainty. There's one more way of handling uncertainty. That's called maximum error. Maximum error, you don't need calculus to do it. You just calculate the maximum that will be off based on your estimates of the maximum error in each of the given quantities. Okay, so very soon this answer would be wrong as your final answer. 186. You need one more equals, and then to 190, and then you'd be correct. Okay, let's look at the next question here from PowerPoint. Piggy bank with 2,608 pennies. How many dollars did she have? This one is, can you just do this one in your head? $26.08. Okay, so that one
but this would be the dimensional analysis of that. How about this one? Now, the numbers here are kind of tricky as far as uncertainty goes. You know, 2608, maybe there's a miscount. That would account for plus or minus. You know, maybe it was around 2608, plus or minus a few due to miscounting. But otherwise, could you have less than a penny? Could you have a fraction of a penny? And so whole numbers like this are usually exact. But it depends, you know, how many people were at the event yesterday? Well, you know, we might say 16 people were at the event, right? What do you mean, exactly, or plus or minus? Is there uncertainty? Well, it depends on how you counted it. So same thing here, depends on how they counted it. Could have counted it, double checked it. This could be exactly 2608. How about this? This is exact by definition. Anything by definition is exact. All right, we're going to be dealing mainly with the metric system, not entirely. Metric system, there's some standard units there, and some derived units. SI is this international system of units. SI units are what we use. SI, you know what the SI unit for mass is? Kilograms. But kilograms is too much for us. We usually work with grams. So the SI unit's kilograms, we work with grams, but grams and kilograms are closely related, so sometimes we'll deviate. You know what the SI unit for volume is? Meters cubed, cubic meters. The cubic meter is too big, so we use liters or milliliters instead. But they're related, so it's not difficult to deal with. Then we have prefixes. There are going to be certain prefixes that you need to know, like kilo and milli. These are very common prefixes. Kilos 1,000, millis 1/1000. All right, so what prefixes should you know? Kilo is good, 1,000 units. Mega is good, million. Giga is good. Giga would be a billion. Tera would be a trillion. So these are good to know. Especially now, you know, you have terabit drives, hard drives, and stuff. Hecto, not so important. Deca is not so important. Hecto and deca, I would, you don't have to bother knowing those. Deci, not so important. Unless biologists use deci a lot, so you might, but chemists don't use it much. Centi, yes, a lot. Milli, yes. Micro, yes. Nano, yes. Pico, yes. Well, pico, where did you hear pico before? The size of the atom's good. Pico. So this is important. So out of these, you don't, hecto, deca, and deci aren't that common. So I just wouldn't bother knowing those, but everything else you should know. Now, coming up with conversion factors is pretty straightforward for the so the typical way that people do this is like this. So if we're looking at 1 micrometer, you know, what is micro? Micro is times 10 to the minus 6. And so 1 micrometer is 1 times 10 to the minus 6 meters. That's one way. And so we could do it micrometers in a meter, or we could do it in micrometers per meter. And so the other way of doing this would be that there would be 1 times 10 to the positive 6 micrometers in 1 meter, just inverted. And so million micrometers in a meter. So normally I think in terms of this way, you know, the way to derive it is like this. Like for example, 1 millimeter is equal to 1 times 10 to the minus 3 meters. Or I would just say there are 1,000 or 1 times 10 to the positive 3 millimeters in a meter. So just flip it. So there are 2 conversion factors that you're going to get for each of these in terms of how you want. There are 2 equivalents of these that you're going to get for each of these depending on how you want to state it. 1,000 millimeters per meter or 1 millimeter per 1 times 10 to the minus 3.
meters. All right, so I said there's a difference between mass and weight. Mass is the quantity of matter, kilograms or grams. Weight is the force of gravity on that. And so let's say a 40 kilogram person, or no, we'll just go 100. Let's say a 100 kilogram person on Earth would be a 100 kilogram person on the moon. But a 200 pound person on Earth would not be 200 pounds on the moon. You know what they'd be on the moon? It's 1/6 that. 1/6 that, because the force of gravity is 1/6 that of the Earth. So 1/6 of 200 would be what? 50? No, 1/6 of 200. I didn't pick an easy number to do, but 33 pounds or so. Is that right? 67 pounds? Something like that. So anyway, they'd be a lot. So weight is the force of gravity on the mass. But chemists, chemists should be talking about, chemists, one day you're here on Earth, the next day you're on the moon. No. One day you're here in this lab, the next day you're in some other lab. Is the force of gravity all that different in somebody? No. Force of gravity doesn't change much, on Earth. Depending on the elevation you go, it can change a little bit, but it doesn't change all that much. So chemists use weight and mass interchangeably. Physicists who might be doing thought experiments here on Earth versus on the moon would be changing things. How do we measure mass or weight? We measure it using a balance. Or a scale, balance or scale. All right, these are the SI units, kilogram, meter. How is a kilogram defined? This is what they call the prototype kilogram, So how was a kilogram originally defined? So that if you wanted to make something that weighed exactly 1 kilogram, how would you do that? Well, I guess you could weigh it on a balance or a scale, but what if your balance and scale is not operating properly and you're not getting exactly 1 kilogram? How would you figure out what weighs 1 kilogram? So that's it. I don't know. I think somebody picked up a rock and called that 1 kilogram or something like that, and that rock has to be stored in a safe.
Isn't a gram equal to 1 cubic centimeter of water?
Not exactly. Not exact. There's at one temperature it does. 1 gram of water is 1 cubic centimeter of water, but it changes. That could be it. Maybe that's it. 1 cubic centimeter. That sounds good.
Because 1 calorie is the amount of energy that it takes to keep 1 cubic centimeter of water 1 degree.
By 1 degree. At 4 degrees. Because water, actually, let me just if you look at the density of water, room temperature. What is room temperature? Room temperature is at 25 degrees C. So what is the density of water? The density of water at 25 degrees C is 0.997, about 0.9972 grams. That's the density of water. It's only at about 4.5 degrees C does it hit 1.00. So if you're at a 4.5 degrees C, then the density of water is actually 1.00. And so the whatever you do, whether it's mass or whatever else you do, actually I guess we're out of time here in 1 minute, But we want something that has a good reference point, you know? And so, what's the difference here? Do you know that the kilogram is locked in a vault in Paris, France? Did you know that? Actually, I'll show it next time. The kilogram standard is locked in a vault in France, and it's this. I think it's made out of gold. I don't know, but that's it. That's the reference. And in order to use that reference, you're going to have to go to France. Use it. Check it. We'll talk a little bit more about this later.